So this is work that I've been doing with 3 postdocs at Berkeley: Simon Napper, Tom Lane, Tim Liu. This is sort of the second, third time I've given this talk. When I first wrote up these slides and I wrote in this title, my laptop suggested a very nice typo, which I've been using since, which is, so you see, and this is very relevant because we 3 postdocs every Tuesday, Thursday, and Friday go into San Francisco, and we disco. This is where we did this, the majority of this work actually. So, and so the idea is that this actually could be happening. There could be axions being produced at the LHC in heavy ion collisions, as you'll see. And so this talk is a little bit about how we might try and crash the party. Okay, so I'm going to be talking about heavy ion collisions, which is lead-lead at the moment at the LHC. The LHC has actually been doing a heavy ion run for the past couple of weeks, but it's not lead-lead, it's been lead-proton, which has a factor of 1,000 more luminosity. But so I won't be talking about that in too much detail, but I will be talking about lead-lead collisions. And the nice thing about this is that these are the 4 major LHC experiments, and all 4 major LHC experiments see lead-lead collisions. So this is ALICE, ATLAS, CMS, and LHCb. I don't know much about lead-lead collisions. I'm coming from this from a different point of view, but so you'll see in a minute why I can be here talking about them. Okay, so the luminosity for the 2015 run at the LHC. This is the integrated luminosity. You see here ATLAS, CMS, and ALICE, and they all have roughly a similar amount of integrated luminosity. Something I'm going to take it as an inverse nanobarn for it's a rough number. LHCb is much less than this. They have to save their detector a little bit. And so most of the numbers that I will give today will be with an inverse nanobarnish of data, of lead-lead data. For the high Lumi run, this is going to go up to about 10 inverse nanobarns. So those are 2 kind of numbers to keep in mind. And so there are 2 kind of extremes of lead-lead collisions. This is one of the extremes. This is head-on collisions. So these lead ions carry an energy of 5.5 TeV per nucleon-nucleon collision. But then there are around 200 nucleons, 208 nucleons in each of these lead ions. And so they smash together. If it's head-on, you get these 200 times 5, 1 PeV fireballs. And these are these beautiful, lovely pictures that you often see of these lead-lead collisions, where the detector lights up like a Christmas tree. I'm not going to be talking about this at all. I'm going to be talking about the other extreme of collisions. So when they're not head-on, when they actually don't touch each other at all, when they're very far away and they interact. And this is called an ultra-peripheral collision. So in here comes one lead ion, the other lead ion is going the other way, and they don't overlap. The impact parameter is large, but there is some kind of interaction in between here. This is this blue star. And these ultra-peripheral collisions, or UPC events, are characterized by the fact that these ions don't break up, the lead ion doesn't break up. Caveat, there's something I will talk about, which is kind of interesting when actually it does do something, and gets a little bit excited, and I'll talk about that in a bit. But these lead ions stay intact. And then there's a very low multiplicity of particles in the detector. So really 1 or 2 particles are made, just a handful of particles. So these are very unique events. And this is I think this is actually a simulation, unfortunately, but this is a simulation of one of these events. And you see there's nothing. There's absolutely nothing in the detector except for 2 tracks. These are I think 2 muons that have been simulated. And so this is a UPC that has created a J-side particle. And so this inside this blue kind of amplitude, if you like, what's gone on is the following. You have a photon that's been emitted from this. This is a lead ion coming in here. This is another lead ion. This lead ion has sort of emitted 2 gluons. 2 is important because it needs to be a color singlet, so it's not to break up this lead ion. And this photon is sort of split into a CC bar, and these gluons give the momentum from this lead ion. And this, I think this is ATLAS. This is showing a plot of the invariant mass the dimuon invariant mass in these UPC events. I'll talk a little bit about how they trigger. In fact, the triggering is very important, and so I'll spend a bit of time talking about how they trigger on these events later on. But you can see a very beautiful mass peak as this LLL goes through around 3 GeV. And these are what these events look like.
They don't directly observe the correlating red ion.
I'll come to that. So they have, I think for this analysis, no. They don't require that as part of the trigger. But yeah, I'm going to talk about these calorimeters they have for doing just that. Because they're kind of cool. Alright, so I guess as my title kind of suggested, I'm going to be focusing on a subset of these UPCs, which come from when you have 2 photons emitted from each of the lead ions. So you can really think of this as a heavy ion photon collider. So out of each of the ions, they come in, they emit a photon, and so I'm going to be considering, all processes where you have gamma gamma going to something. And so why is this particularly interesting? Well, so the lead has a charge, Z. Z for the lead is 82. And each of these vertices, because they have an electromagnetic charge E, comes multiplied by this Z. If these photons see all of the protons inside this ion coherently. And this is an important thing, and I'll talk about the conditions when this is true. In fact, generally the conditions for them to be coherent are the conditions that we want, in the sense that it's going to be a UPC. There's going to be no extra particles in the event because this lead ion remains intact. When the photon starts to see inside the lead ion, you start to break it up. And so these photons will see this charge coherently. So in this amplitude, you get a z squared. You square the amplitude, this process will go as a power of z to the 4. And z to the 4 is 5 times 10 to the 7. And so there's a huge enhancement in this amplitude, this 10 to the 7, 5 times 10 to the 7 enhancement in the amplitudes where you have photon-photon going to something, coming from the fact that this lead ion has a very, very large charge. Okay, and this is the sort of signal process that I'll be talking about. This is the production of an axion-like particle. So it's produced by photon fusion, and then we're going to consider the case where it just decays back into photons in a minimal scenario. And this is not a new idea. I mean, people have thought about producing such particles in photon-photon fusion before. RIC, for example, in heavy ion collisions, again using the ions of the cloud RIC to emit the photons. So, for instance, these papers have thought about this kind of idea. So the idea itself is not new, but this is the first time it's been analysed at the LHC. And then, in fact, I'm just going to talk about Atlas and CMOS detectors. Okay, so RIC called this kind of process a gold flashlight because they were colliding gold ions. So in some sense, this is the LHC's lead flashlight. And it's the world's most powerful flashlight. I put a star here, and this is in the GeV range of energy. That's because it's actually the only flashlight that we have in the GeV range of energy. But so we have the world's most energetic, if you like, flashlight. And so the question is, can we do some cool stuff with it? And so here's the interesting thing, that lead-lead collisions are typically not optimized for beyond the standard model searches. So the lead-lead runs are not thought of as looking for physics beyond the standard model. Head-on collisions, for instance, studying quantum plasma. And this is because there's a lower luminosity and there's a slightly lower per nucleon collision energy as well. And so there are two things that we're going to win with in this game. One thing is this huge Z to the 4 enhancement that I already mentioned. And the other is this extremely efficient background rejection. So as I showed you, these events are very, very clear particles. They're very empty. And so this is something that you can use to cut very hard and kill background. You can require very, very little activity in the detector. And this will be extremely efficient, as you see, and this will also be something that gives you sensitivity to things, or in this case, a thing that you cannot get in for example, a PP. Okay. So now I'm going to talk for the next sort of 5 minutes about just a quick rough estimate of what kind of mass reach we're talking about. So I showed this process with an axion that's going to be produced. What kind of mass axions am I thinking about? And how high an axion mass can you go? And this is a question about how much center of mass energy your photon-photon collider has. So I'm asking, how hard can these photons be? How much energy can they be? How much energy can a lead ion radiate without breaking up? And so somehow the maximum energy is given by the highest frequency, which does not resolve in this lead ion. So one, I don't want the lead ion to break up, and two, I want all of the Z protons inside this ion to be seen by this photon, so I want this to be coherent across the ion. And so if a lead ion has a radius of r, then the maximum energy before you start resolving the structure of this ion goes as 1 over r. And so this is in the rest frame of the lead ion. Of course, now you have to consider this in the lab frame. And so if you boost back to the lab, so this direction doesn't change, but you get Lorentz contracted in the boost direction along the beam pipe. And so these things look like little flat disks that you're climbing two flat disks together. And so this picks up a gamma, a Lorentz gamma factor, and so the maximum energy is gamma over R. Or equivalently, I take a photon in this frame and I boost it and I pick up that Lorentz factor. Okay, so some typical numbers. Let me give some typical numbers for proton and for lead. So this is B min is I'm taking, I guess 2R is maybe a more fair length scale. So for the proton, 2R is about 1.6 femtometers. For lead, is about 10 times as much. The energy for a nucleon is kind of comparable, but so this gamma boost factor is around something like a few thousand, 5,000 or something, 3,000.
Is this the same estimate you would get if I used the excitation energy of the nucleon instead of 1 over r?
So that's kind of MEV-ish, which is kind of R-ish, so 1 over R-ish, so it's pretty much the same energy scale. Yeah, I think that's right. Just nuclear. Yeah. Okay, so this translates into 2 times the maximum frequency of these photons, so this is twice because I'm considering the center mass energy of these 2 photons. It should be around 1,500 GeV for the proton case, and for the lead case it's like 10 times smaller because this radius is about 10 times larger. And this 1,500 GeV is why you can take gamma gamma to a 750 GeV resonance that decays back into gamma gamma. This is very high mass energy, actually, surprisingly high. Whereas this is 10 times lower, so you're losing something by going to lead, but you're gaining a Z to the 4th charge. So we'll see how those kind of play off.
So basically it's saying you're emitting a low energy photon that is boosted by the energy.
Exactly, that's right. So in the rest frame, this photon is low energy, but it's getting boosted by a factor of 1,000 to 5,000 into the lab. Okay. So let me go back a second actually. So on this slide here, I have this Z times E. So the amplitude for this process, your expansion looks like Z squared alpha. When Z is 82, this is a number that's significantly larger than 1. And so somehow you're kind of in a weird situation where you have strong abelian gauge theory. And so a perturbative expansion, a defined diagram of expansion is not going to be a very good thing to do to try and estimate what the flux of these photons are. It's not like a PDF. It's not like you would do a calculation for a PDF and evolve some spinning function like this. So you're in this kind of regime of strong QED. And so I'm now going to talk a little bit about a calculation that you can do that sidesteps having to do some kind of Feynman diagram or perturbative expansion in Z squared alpha, which would clearly be a bad thing to do. And so this is a kind of semi-classical approach to getting what a flux of photons, if you like, a PDF of photons that are coming from these lead ions. And it's a really neat idea. It actually harks back to Enrico Fermi. So he came up with this method. It's called the method of effective photons. And so these are the two ions. We're sitting in the lab frame. This one's going this way, this one's going this way. So they're these flat disks. And when you take these ions and you boost them into this frame, the Lorentz boost forces the electric fields to kind of fan up. And they fan up into this big disk shape. And so you get these two kind of, if you like, disks of electric field that are whooshing past each other. And the idea is simply to replace this electric and the magnetic fields with a flux of photons. So it's kind of taking this, there's going to be a classical E&M calculation, and then there's going to be a quantum kind of approximation, an effective quantum approximation, to turn it into photons, which we want to have because we want to be able to calculate the amplitudes. Okay, so these guys are rushing past. So you can imagine sitting at some point here. So if I'm sitting here, what does my electric field and what does my magnetic field look like? So this is actually this is a problem in the back of Jackson's E&M book. So at some point here, it turns out that when you take this charge density, you have some spherical charge density in the rest frame, and you boost this into the lab frame, some v, some velocity v. As v approaches c, so as this thing starts whizzing past you closer and closer to the speed of light, the electric fields and the magnetic fields you see at this point start to become the following limits. So the magnitude of the electric field starts to become equal to the magnitude of the magnetic field. The electric and the magnetic field become perpendicular to each other. The electric and the magnetic field also become perpendicular to this velocity. And so these are exactly the form of the electric and magnetic fields of the photon solution to Maxwell's equation, propagating photon. And so you can see where this equivalent photon approximation is going to come from. Because in this super ultra-relativistic limit, the fields really does. You sit here, you get this electric field passing through you, it's like a little blip, and that looks more and more and more like a photon as this speed approaches the speed of light.
Are you using a point particle approximation?
I'm going to talk about the approximations that I make in a second. So I'm going to go through actually a derivation with a point charge. So this thing is just a point charge. And then I'm going to talk about other approximations that we can make, and in fact we do make in the form of a public code that's already been written.
I was wondering, is that a good approximation? Because I might think that the leading thing would be coming when we do sort of a blazing collision.
That's right. So there's
point charge approximation.
It depends what you mean by leading. So leading. So I'll show you that I'm going to cut out that area of the phase space. Yeah. But all those kind of approximations are quite interesting, actually. But at the end of the day, you get something that agrees incredibly well with experiment. Okay, so once you do this, now you know what the electric and the magnetic field look like, you can just equate the energy fluxes of this calculation that you've just done, the classical E&M calculation. So this is you can define a pointing vector, and S is just E cross B, and you can equate this. So this is the energy flux. I've taken now some transverse plane, and this is some small element in the transverse plane, dx perpendicular, if you like. So I'm imagining sitting here. There's a plane that goes through the board, and integrating over all time from minus infinity to infinity, so this ion is whooshed past. And I'm integrating over this pointing vector, which is giving me the energy flux in my classical calculation that's going through this plane, but I'm just being differential in the coordinates on this plane. And I can equate this to the object that I want to define, and that object is this photon flux. So I'm imagining that now there's going to be a flux of photons, and so this is the number, if you like, that are going to go through in the time it takes for the ion to go to pass through. And so I multiply that by energy, and I integrate over all energies, and I've got to equate these things. So this is kind of the link between the classical calculation and the photon flux. All right. This is also known as the Weizsäcker-Williams method. There's another name for it. And so this is the answer that you get if you assume a point charge. So now I assume that there's no radius here, there's no spread charge, it's just a point. This is the formula that I get if I go through this exercise. And this is a Bessel function here. B is the distance, the transverse distance from the ion. E is the energy of the, so this is differential in both energy and this transverse distance. So this gives me the flux at a given distance for given energy. So this is the flux of photons at some point up here. Gamma is the boost factor, you see this as Z squared. So this really can be interpreted as a little bit like a lot like a PDF, and you can use it as such. Oh, I actually have I have a plot of this, okay.
So how do I interpret just physically, and I'm a little confused about the flux depending on U. I would have thought that it would be some angular thing or something. See what I'm saying?
So we're getting to we're approaching the ultra-relativistic limits. There will be small parameters away from small terms that are neglected away from that limit, so V over C. Or that kind of angular parameter that you're talking about. But and the reason is that these things are the reason it depends on the distance is because these field lines, as you go further away, are stretching out a little bit more.
It's actually
so it's weaker.
I see. It's
yeah, but of course I can't take the strict limit where everything's just a flat plane. So it's kind of.
Okay.
I forgot that I put in a plot of this. Okay, so this is a plot of this. So this is B, and this is E going along here. So you can see that as I bring down B, this thing actually blows up. So for fixed energy, I can look at this function as I bring B down, and it's going to blow up because this Bessel function, as this argument goes small, goes like 1 over this argument. But for fixed B, there is a final.
1 over gamma squared.
Sorry?
Why does it go down like 1 over gamma squared? Is that easy to understand?
That is, so there's a playoff here, because this makes it look like this is grading into 0, but because the gamma is in here as well, this is actually blowing up.
Wow.
So if you just look at this term, it feels counterintuitive, but it's the combination of the two. So actually, as you intuitively expect, for larger gamma, you get a higher flux. So if you just kept everything else fixed, you increase gamma.
Well, what is the behavior of K1 for small argument?
1 over. Yeah.
1 over.
It's 1 over X.
So the B squared and gamma squared cancel, so basically it goes like 1 over B squared.
That's right. Oh, that's right. Exactly. That's great.
That makes sense. It's just a two-dimensional field.
Yeah.
Yeah, exactly. Yeah, that's right. Okay, so now armed with that that's for a single ion. That's the kind of flux coming off a single ion. Now I'm changing just the way we're looking at this, and now we're looking down the beam pipe. So one of these ions is coming out, and one of these ions is going in, and the field lines look like this. Now you can obtain a photon-photon luminosity. So I'm going to consider some point here, which is a transverse distance B1 away from this ion, a transverse distance B2 away from this ion. Okay, and then I'm going to obtain the luminosity at this point for a fixed center of mass energy, S hat. I've got a delta function here that tells me that S hat is equal to 4E1, E2, so that tells me that what E1 and E2 are constrained to be. And then I can integrate over all B1 and all B2 and all E1 and all E2 to obtain this luminosity function. And so here these N, E1, B1 and N, E2, B2 are just the functions that I defined here. Or this is for a point charge more generally, they take a little different form, we'll talk about that in a second. But I can integrate them. I can integrate over all B1 and all B2. Notice you're also, in doing that, I require B1 and B2 to point to the same point. So what I'm also doing really is I'm also integrating over all impact parameters here. So what else is in this integral? Well, so here there's a p, which is a no breakup probability. So this p is some function that you have to put in, some phenomenological function, that defines probability that at this point in B1, B2, so you see this is actually only dependent on B1 minus B2, so on the distance between the ions. There's some probability that they will not break up. So let me now talk about some approximations. So this approximation of a point charge is fine if I restrict this B12 integral, so over B1 and B2, to be greater, so the modulus is greater than R. So this means always that this point will lie outside the radiuses of these ions. So the point charge is fine. And whether this is a good approximation or not, that you have this hard, this is called the hard shell approximation. So whether that's good or not is a separate issue, I'll show you in a second. But this clearly means it's okay to have a point charge. And so if I do this, and then if I also assume that there's no breakup probability is just 1, as long as B1 minus B2, this thing, doesn't equal less than 2R. This really is a hard shell model. These are two very reasonable things to
Just coming back to this point about this, so I still think it would be important to know whether or not this integral is then dominated by these equal to R.
Very good, yeah.
Right? If it's not, then it's...
So the high energy tail is dominated by that. But the bulk of the luminosity comes from not that region. So it comes from the larger phase space that you have outside that. So yeah. So in some senses, it depends what S hat you're interested in. So these are two very reasonable assumptions. If you take this just to be greater than 2 times R, this means that whenever these things overlap, they're probably going to break up. There's going to be hadronic strong interactions. Also, if this point was inside one of these ions, this is what we're asking for the photon-photon collision, if you like, to happen inside an ion. So you would expect that to be a bit weird, or certainly break up the ion. And so these are kind of reasonable models. However, I think people have been doing this for a long time and have put in many different approximations. So putting in a charge form factor, nuclear form factors, more complicated breakup probability functions that are, I guess, phenomenological. And they also, this whole setup here, it's neglected any transverse momentum of the ion system, but you can also put that in. And so this is a comparison with a code that we actually use at the end of the day to do all this. It's called Starlight, these authors. And so this is a comparison in this luminosity function. So we change from S hat to M gamma gamma here. Between the hard sphere model that I just described and a realistic Starlight calculation, Monte Carlo. And you see the agreement is actually really, really quite good over this mass range, which is kind of nice. But at the end of the day, we use the more realistic one because that gives some extra features, such as a PT distribution to the gamma gamma system, which is something you might be interested in for background projection, which I'll talk about in a second. All right. So this is a question that is one of the first things that people think. Well, this sounds great. We know that the Higgs covers the gamma gamma. Can you do this to the Higgs? Can you do this for the Higgs? Can you create a Higgs boson like this? And this has been thought about before. Obviously, in the 80s. Jackson, Bob Prime, actually, did this calculation. So let me go through it for you. So this is the cross-section for gamma gamma to Higgs. It's going to depend on the luminosity, this gamma gamma luminosity, evaluated at this point MH. And then there's a matrix element for gamma gamma to Higgs, which by crossing symmetry is the same as the matrix element for Higgs to gamma gamma. So I can relate that matrix element to the decay. So this is the decay width for Higgs to go to gamma gamma. It's by crossing symmetry. And then there's some phase space factors that come from sort of converting that into a decay width, but the fact that actually calculating cross sections, and you kind of divide out, and you end up with this numerical factor here, divided by MH. So, just to estimate this luminosity at 125 GeV is somewhere like 10 to the minus 3, 10 to the 3 nanobarns-ish. This is a nanobarn, should have said. This width is, well, the width of Higgs is sort of MeV-ish, times 10 to the minus 3 for the photon decay. This mass is 100 GeV, and this numerical factor is about 100. So the hundreds cancel, you get an MeV over a GeV, so you get kind of a 10 to the minus 6 times 10 to the 3 nanobarns. And so this whole thing comes out as a picobarn. But as I said earlier on, one of the numbers that you can have in your mind for the end of the high Lumi LHC run is 10 inverse nanobarns. At the moment it's 1 inverse nanobarn, high Lumi 10 inverse nanobarns. And so a picobarn cross section times this is not large enough, right? So you don't get 0.01 times. It's not too far off. It's only a couple of orders of magnitude too small. So it's tantalizingly close, but it doesn't work, unfortunately. So the answer is you can't quite do it.
So that was for what mass Higgs?
That's 120. That's the standard. And in fact, over a mass range, light. I mean, this was done in the 80s, so the plots for the whole mass range. In fact, across the whole mass range, it doesn't. Okay, so.
But of course, if you had another Higgs that had higher.
You have to change a bunch of stuff in this. You see, yeah, you have to change this basically. And leave that to go because this is fixed. As you get to higher masses, of course, it's going to get worse. So.
I think lower masses.
Oh, lower.
Of course, is where you're headed.
Then exactly. Then you might be in shape. I have a slide here about which ions are best. So this is something that I took. Actually, I've got a reference from a review by Bauer. So this on the left-hand side is LHC energy. So ignore the right-hand side for a second. And this is comparing the luminosity as a function of W, which is the center of mass energy. And this is instantaneous luminosity for a bunch of different ions. For lead, so heavy ions, argon, sort of medium ions, and protons. And it also has the E plus E minus for comparison. So the E plus E minus curve is this one here. This is LEP, which dips at the maximum LEP energy. You can't get more energy than your electron beams are on your photon-photon. Now this is not quite the full story. This thing is multiplied by a number, LAA, which is the luminosity that you can expect at a given ion-ion collider. So when I first saw this plot, I was kind of annoyed. I was like, I really don't want to know this number. I don't want to know the kind of design of a particular collider. But it's interesting. It turns out that there's a reason why this is included. So for here, for instance, argon has a luminosity of 5 times 10 to the 29, whereas lead has a luminosity of sort of 5-ish times 10 to the 26, 3 orders of magnitude less. The ratio of the Z squared, so 18 squared to 82 squared is about 400 difference. So you'd expect that maybe this argon would be an order of magnitude-ish better than the lead. This is in fact what you do see. So this solid curve here is the lead, this dashed curve here is the argon, and there's kind of slightly more than an order of magnitude, and that's because argon is lighter mass. So lighter mass means 1, you have a higher collision energy, and 2, the maximum kind of photon energy that you can radiate still being coherent is larger. But it seems artificially, these luminosity, sort of design luminosity, the argon luminosity and the lead luminosity are being introduced. So I'll get to that in a second. There's a really fun reason why that's important, and why it should be included in this kind of fair comparison. So you can see actually that lighter ions are somewhat better than lead. I've heard, it's true, I don't know if this is true or not, but I've heard that at the LHC, the guy who could change the ion that you put into the accelerators is retired. And so now no one knows how to switch from lead to something like. I don't know if that's true or not, but that's what I've heard is true.
So once again, why is the argon better than lost?
Yeah, good. So the argon is better for a number of reasons. So first of all, you would think it would be worse because the charge is much less. There's a factor of 400. This goes like Z squared. So 18 squared to 82 squared is 400. However, they're multiplying by this design luminosity for the argon-argon collisions versus the lead-lead collisions. So for the argon-argon collision, there's 3 orders of magnitude larger number here.
okay.
So,
My eyes are not.
yeah, sorry, it's,
All
it's
right,
very simple.
okay.
So this is 10 to 29, this is 10 to
okay,
26.
okay, I got
So
it.
that overcompensates by the order of magnitude. And as I'm saying, there is a reason why they do this.
Is your sort of Fermi or life cycle variance approximation somehow an expansion in 1 over z or something? I mean, for protons, it wouldn't be good.
For protons, it would not be good, no.
So what
That's
is
right.
it? So it isn't. Can I understand it? It's some sort of systematic expansion in
I
large z, or
don't think large C, that's an interesting question. I have never seen anything in the literature about 1 over z squared expansions. I don't think so, right? Because I think the z squared always comes with an alpha, so maybe it is a z squared alpha. But it's not really perturbative at all. It's not perturbative in that coupling constant at all. It's just you've just done the full thing, right? It's a full strong.
It somehow should be better in large z.
That's correct, and it is better. So, yeah, whether you can interpret that as a 1 over z, z, I don't know. Good question. All right, so to the search for these axion-like particles. So this is the Lagrangian that we're just assuming. So there's this A is the axion. It's going to have a mass, and it has this coupling to electromagnetism. So just some pseudo-nanodorsal boson from some spontaneous group of symmetry, for example. This is the diagram, and as I've somebody to kind of said what mass range we're interested in, it's kind of a GeV mass range. So this is collider mass range. And this is a plot that I just took from this paper here. So this is the axion mass that goes from something like 10 to the minus 12 or 10 to the minus 15 electron volts up to 10 to the 12 electron volts. This is the coupling. This is essentially 1 over lambda that we're using in this Lagrangian. And so we're interested in this regime here, which is the collider. This is the only limits that are placed on this model here in this region are from colliders. So there's some LHC and some CF bands. Okay. So it's this region of parameter space that we're going to be probing.
So the left bound, the number there is.
I'll show you. We also redid these bounds because this plot is very logarithmic and difficult to. This is around between 100 and 1,000 GeV. Okay, so we can use the luminosity that I just went through describing how we calculate that to get this cross section, because we know what the cross section is in LHC. So here's how to trigger these things. This is kind of the experimental important points. So we were made aware of 2 new triggers prepared. There's a CMS UPC working group. This analysis still hasn't actually appeared, but we know what we've been talking to them, so we know what they've been doing. They have 2 triggers, so they require 2 photons with energy greater than 2 GeV and no hadronic activity in one of the forward calorimeters. So this is saying that in my central calorimeter, I just require 2 photons. There's some photon ID, but essentially you can imagine just hits in the calorimeter of 2 GeV of energy, and they're completely vetoing on any energy activity in the forward calorimeters. And normally, with any kind of normal interaction, so non-UPC interaction, you're going to get some soft hadrons, some strong particles that are going to go forward in everything. And so they're really cutting down on this strong activity to trigger on this UPC event. They also have a similar one where they just require 1 photon with energy greater than 5 GeV, and then they say no hadronic activity on the forward calorimeters. So really, you get into this lovely situation where it's like lab. Really, these events are as clean as lab, cleaner even, but you have now LHC ray detectors. So it's kind of cool. So let me now go over in sort of the next 10 minutes over the backgrounds you have to consider to this process. And so there are 3 major backgrounds that there are 3 major backgrounds, and we consider these. So this background, central exclusive production. So this is a diagram with protons. I'm going to talk about how we scale this to lead. Okay, so the lead will come in here. There's a gluon fusion, some loop of charged particles, so quarks in fact, and then gamma gamma come out of this loop. Again, because you want this to be not to break up the ions, there's going to be a gluon exchange between here to make this a color singlet, so you don't have to break up the nuclei.
Sorry, can I ask a question I should have asked earlier?
Yeah.
Sorry, back when we were talking about argon. Does the lighter nucleus also give you higher energy for your beam?
Yes,
It's proportional.
that's right. So you gain that
you
as
get a
well.
boost factor.
Exactly, because the coherent, the argon about the mass reach and make.
I mean, it seems like it would be very interesting. I mean, just because you point out, this is as clean as lab. Of course, with the caveat that you don't know the beam energy, so that's right. I mean, you don't have a single beam energy; you have a distribution. That's fine. But if you could get, it seems like you can get pretty. I mean, you can get impressive sounding luminosities, but with low energies. I mean, has somebody thought about if you try to make? I mean, I'm sure somebody must have thought if you want to make a photon collider in this way.
Yeah, I mean, this is what people talk about when they talk about photon colliders. And you do know your beam energy. It's not fixed. So for each thing is different, but each event you do know your beam energy. You do know there's no mass collision.
Right, because it was fully reconstructed. It varies event by event, but you can reconstruct it.
In principle, if in principle, if you can, that's right. So if you can time, so it's in principle measurement. You can also measure the energy.
It's sort of between the hadron, because you can do the forward. There's no problem in measuring the. No, okay, I have to look at it. But anyway, finish it now. I stopped reading.
No, but actually, what I think would be really cool. I mean, that CMS have released data. They have this data set from Pb collisions, I think about most of Pb collisions, which is presumably a complete mess. You won't have no events. This would be a really cool data set to release. The UPC events where it does look a bit like labs. So you can imagine really just a few particles and each event with 4 vectors on it. So I think this would be a really nice thing to have.
That's what they're really cared about. Other people do it.
They do care. Well, okay.
It's a long way, but it's a long time.
Moving on. Light by light scattering is another background. So this is the kind of similar to this, but it's photon-photon initiated. So this is really irreducible in some sense. You have gamma gamma goes through a loop of charged particles to gamma gamma. And then there's a background where you have fates, so where you actually have E plus E minus production, and this electron is typed as a photon by mistake. So you pay twice because you have to mistype both of these things. It turns out that these still actually do constitute backgrounds. So let me go through this central exclusive production first. So here we used a Monte Carlo program called SuperCheek. These authors developed. And they developed this in proton-proton collisions. So in proton-proton collisions, they have theory predictions given by these bands here. And CMS has published an upper limit using the 36 inverse femtobarn proton-proton data on this process. Now, there is no available tool, program, nor theoretical calculation of how best to scale this up to lead-lead. So the most naive scaling would be an A squared scaling, because there are A of these protons in each of your ions, and so A from this and A times this would give you an A squared. We think this is actually a little bit too aggressive to scale by A squared. We actually think maybe an A to the third is maybe more reasonable. So if it scaled as A to the 2/3, that would be saying that this is a surface phenomenon. So this actually only really happens between protons if those protons are sitting at the surface of the ions. Then, of course, because your ions only touch at one point, this is not really a surface, it's actually a point kind of scaling that you should use. A to the third doesn't actually matter. Even the A squared scaling, so the most conservative case that we took, we find this to be small, essentially negligible background. It's also largely reducible. So here is the spectrum of the PT gamma gamma. They said that the actual program we used to give the signal, which is in green, produces. And this is the purple signal, is the PT gamma gamma from this background process. And they have different scales. So the scale of this PT gamma gamma is 1 over the radius of the proton, because you're really taking the gluons out of a proton, not out of the nucleus, if you like. Whereas this scale is 1 over the radius of the lead. So you could imagine if you really wanted to cut on this, you could imagine cutting on the PT of a gamma gamma system at some point to reduce this even further, but we find that it's not. We estimate that it's not actually needed. And this will be backed up in a second by an actual
This is
section.
a region where the two gluons leave the lead untouched, right? At very small momentum transfer
Yeah,
and so forth. That you're sure that's not important.
yeah, we think this is too small. So, I mean, you mean when these gluons are pulled out of some kind of internucleon region, or?
No, just
No.
the. Well, I guess actually the lead would.
They have to be pulled out of the proton. They have to be pulled out.
We're getting into this domain of a pomeron or something like that.
Yeah, it's very similar to a pomeron, actually. Yeah.
Neural vibrates. And
It is-
there are
yeah,
models where
that's
the
right.
pomeron has the whole nucleus as a coherent source with the momentum transfer on the pomeron is small.
So that would be interesting. So if it was coherent, then of course this would go as 84.
Yeah.
But I think that would be for very, very small momentum.
Yeah, probably.
Yeah, it's something that we're worried about a little bit. Let me show you an atlas measurement, if you like, or non-measurement of this. And so we feel safe because of that. But, no, this is kind of stuff that we did worry about because these exactly pomerons and but this is not pomeron calculation. I mean, this is some conservative calculation of things. All right, fates. So this E plus E minus has a huge cross section. So this, I was talking about cross sections that there's a kind of inverse nanobarn luminosity, and we talk about nanobarn cross sections. This is a millibarn cross section. So assuming even a 1% fake rate, so I square this fake rate to get both of these typed as photons. This still gives something in the sort of 10 to 100 nanobarns region. So this is something that we would expect to see these fake processes with an inverse nanobarn data. Here's a brief aside.
Is there any reason why you're not considering the jet fading polymer? At least in Higgs case, they're asymptotic.
The which, sorry?
The jets,
The jets.
yes.
Final state, you mean?
Yeah.
I'll come back to that. So the reason is a triggering reason. So it's the fact that we know that this trigger is designed by CMS to actually pick up on these events. You have to be able to trigger to be able to get this. And so, but it's a good question. And so actually maybe in a second now. Oh no. In my next little sidetrack, I will talk about that. So this is just a brief diversion. I found this out a couple of weeks ago. Spencer, who was at LBL, who produced this program that we're using, gave a talk, and he mentioned this really cool thing. So it's kind of related to this background. So here you produce E plus E minus. It's not like high PT plus E minus. This is a much, much softer process, but you can sort of imagine this diagram just to help guide you. So it's a very, very soft electron, and what happens is one of these electrons gets caught over time, gets captured. And so you have this process, lead 82 plus lead 82 plus goes to lead 81 plus, the captured electron, plus lead 82 plus positron, which disappears. And the magnets bend this differently because it now has a different charge. And so this is a simulation of how this happens. So this is the interaction point here. And so you see here, this is the beam width of all these lead ions coming here. And you see at some point, because it has a different charge, this lead ion, this 81 plus ion with the captured electron, gets bent. It gets bent out of the beam, and it hits the magnet. And that the rate at which the energy of or the power that gets put into this magnet from these kind of processes happening is of the order of 10-ish watts. And this is high enough to quench this magnet. And so there's actually a limit on the luminosity from this process that comes because you don't want your magnets to quench. The amount of power that you dump into them from this process is a limiting factor in the luminosity. So when I showed those plots earlier comparing different ions, that luminosity was really a maximum luminosity that you can go to because of this process. You cannot go higher, otherwise you'll quench your magnets. And I think that's kind of cool. I would really like to do something with this. Imagine the capture of some kind of mini charged particle or something. So this thing, you can imagine this thing being producing atlas, and beam it around and attack CMS with it, because by the time the charge, the mini charge, you can just shoot off and hit CMS. Anyway, similar thing happens actually with this process, where you just have some electromagnetic interaction here, but you excite the lead ion. This happens around a third of the time in these collisions, and so you can imagine lots of photons drawn here, because really this is z squared alpha, so this is a non-perturbative process in some sense. And so this happens a lot. This then de-excites and ejects a neutron, again a different mass, so it's going to get bent differently. And again you get this quenching. Okay, so that's what I was saying. These numbers that I showed earlier, these maximum luminosities, come from this. So with a lighter ion, you can actually go to high luminosities, because the cross-section for this process is considerably smaller. To end that little brief discussion, let me talk about the final background, which is this light-by-light scattering. So this is a very recent paper. This is a conference note at Atlas, where they actually observed this background, light-by-light, for the first time. And so this is Atlas, not CMS. They have a slightly different trigger, but it's essentially the same. I think I'll actually have this page. Yeah, so they have they look for some amount of energy in their central calorimeters, and then these two hits. This is a minimum bias trigger scintillator, I think. This is essentially a very forward calorimeter, and they require basically no activity. So it's again a veto on any kind of forward hadronic activity. So again.
So can I ask about that? So,
Yeah.
so what kind of accuracy and at what kind of center of mass energy are they extracting trying to do on what light-by-light scattering?
Let me show you the plot in two slides.
Okay, yeah.
So this is, I think you asked this question actually earlier. So this is another little aside that I wanted to go into. These are 0-degree calorimeters, which they have both in Atlas and CMS actually. And so these are calorimeters that sit 140 meters away from beam interactions. The interaction is up here. This is the beam pipe. And then you see here the two proton beams being split. So one proton is going through this beam, one proton is going through this beam. So that's the splitting point, and they get bent differently. So at this splitting point, in between where the beam sort of splits into these two little things, they put some layers of scintillators. This is the 0-degree calorimeters. It really is 0 degrees. And so any neutral particles will not be bent. And so they will just go shooting straight down the middle and be detected by these things. So you can see, for example, the neutrons. When you have that excitation process, so a third of these UPCs, you excite the nucleus, de-excites, it releases a neutron. That neutron goes straight into this calorimeter, and they can see that. So that's that process there. They actually didn't use this to trigger. So Atlas, for this light-by-light search, did not trigger with this. They just, the triggers that I showed earlier were enough. They actually, I think they did use this to estimate some trigger efficiency for this.
So only Atlas has this?
So no, I think CMS also has this as well. Yeah, this is different to the, because I was familiar with the Roman pots that CMS have, which are very high rapidity, but this is really 0. This gets to 0. And I think this comes back to this question that you had as well about why might you not look for jets. This could be a really cool trigger to see two of these, so neutron in both of these. So you know there's been a sort of UPC event that's happened, and now not worry about the trigger on the calorimeter, and just see what you see. And so there you can imagine, so for instance, going into B-jets might be an interesting thing. So particle decays into B-jets. Can you now trigger on this? I think this is something that could be interesting. Studying potentially. Okay, this is the Atlas discovery. So they have a 4.4 sigma observation of this. It has a sort of 50 nanobarn cross section. So again, in the region of nanobarn, tens of nanobarn-ish that we're concerned with. This is the mass range that they observe over. So they go down to 6 GeV in mass. For some reason they bin this in 3 GeV bins, which is how they all go down. 6 GeV.
Does this have any impact on G-2?
It's completely the wrong. I mean, we wondered about this. So can you measure this and then somehow scale it down to G-2 energies? And it's GeV. So. You're interested in this diagram when these external links essentially go to 0. Yeah. No, it's cool. I mean, we wondered about whether you could do a measurement and extrapolate. I think probably the uncertainty is
even 1 GeV.
It would be nice, yeah. But that might be something as well that you might think about, why their trigger required 6 GeV, I guess, of energy in the first place. So you would wonder whether you could, not require that, but then and just use these ZTCs. Oh, by the way, this is they also consider the backgrounds that we consider fakes and this set of central exclusive production, and they essentially have a non-observation of central exclusive production. So we're reasonably happy with the fact that we correct this. But we're happy to be. Okay, those are the backgrounds. Now inject the signal. So this is the example of 2 signal injections, one at 15 GeV and one at 40 GeV for this axiom. So essentially the nice thing about this is that above sort of 15 GeV, this is one event with 1 inverse nanobar. It's essentially like a background free search. So if you see something out here, you have it. Otherwise, we just look for a bump on a forward background. So these are the 3
Do
backgrounds.
these signals assume 100% branching ratio?
100% branching ratio back together. And I think this is the sort of a lambda of sort of 10 to 3 GeV. All right. So this is the final plot that I want to show you. This is the projected sensitivity for the LHC lead-lead collision. So this is the axion mass here. It's linear this side. It's logarithmic this side. And I'll go for a second these existing limits, which is we also re-derived these and sort of updated them or did them the first time. And then I'll talk about these 2 curves, which are accepted the projected sensitivity for the LHC. So this is a limit coming from LEP. So we went back to some LEP papers. And so this is a 2 photon search. But the interesting thing about this search is that they actually didn't put any isolation criteria on the photons. And so this gives a limit from this process here, E plus E minus, goes to photon, axion. Because this axion mass is very small, these 2 photons are going to be very collinear. And so these pass the cuts, in fact, in this mass range, to look essentially like 1 photon in this search. So this, we can translate that onto a limit. There's a similar LEP search, so Opal search for 3 photons. This is the same diagram, but just higher mass, so you open up the decay of the axion. Then there are some LHC searches. So this is a not exclusive. So this is when you break up the protons. So you have quark, anti-quark, photon, axion, and you look for 3 photons. This actually came from, I think, a search. We cast a search for Higgs going to 2 axions going to 4 photons. But they only require 3 photons, so we can use this to set a limit. And then this 2 gamma process, which is a kind of standard LHC one where you have, as if you like, photon PDFs from inside the protons, creates the axion and decays back into 2 photons. All right. And so this is you see that the sensitivity from 1 inverse nanobar of data and 10 inverse nanobars of data, the high lumi, beats these, which is kind of nice. And so just for your eye, this is an actual limit from a search done by CMS with 36 inverse picobars of PP data, so the very low luminosity PP data. They actually looked for 2 photon final states in this, and so we could use this to set a limit. But you see here, lead clearly does a lot better. And the final thing that we can now add to this, since our paper was out, is this atlas result for light-red light scattering came out, so we can actually now recast that and already set a limit. And so that atlas used about half an inverse nanobar of data, and so you see actually it's kind of nice that it's roughly where we would actually expect this. The sensitivity that we estimated is pretty much exactly what we get using recasting this search. So it's half the data, but here we slightly overestimated the efficiency of triggering on these low PT photons. Probably this can be much improved actually, but okay. And in principle, probably, I mean, they didn't show it on this plot. For some reason, they cut off at 30 GeV, but presumably they didn't see anything above 30 GeV. So actually, we should be able to extend this line really up here. Okay, so that's it. So it's one little neat idea, I think. And the nice thing about it is that as far as we're aware, this is the only place that heavy ions can actually better the PP program for PSM. So that's a kind of nice thing for heavy ions. Okay, thanks for listening.